Welcome to my video, and in this video I look at the concept of diagonalization. The concept of diagonalization. Diagonalization basically is the process of diagonalizing or transforming the state matrix into diagonal form using a transformation matrix P obtained from the eigenvalues of the matrix or the state matrix A. The requirements for the concept to be applied are that the matrix A must first be written in controllable canonical form and must have distinct eigenvalues. So if the matrix A has distinct eigenvalues and is written in controllable canonical form, it is possible to obtain a transformation matrix P using the eigenvalues of the matrix A that will diagonalize or transform the state matrix A into diagonal form. Suppose A, our matrix A or our state matrix, suppose our state matrix A is an n by n matrix written in controllable canonical form as the matrix A is given by 0, 1, 0, all the other terms being 0, and 0, 0, 1, all the terms being 0, all the way up to 0, 0, 0, until the last term is a 1, so that we have a diagonal of 1 along this line. And then this last term is negative an minus 1, negative an minus 2, negative a1, where an all the way to a1 are the coefficients of its characteristic equation. If A is written in that format, and suppose the eigenvalues of the matrix A, the eigenvalues of the matrix A are lambda 1, lambda 2, all the way to lambda n. If A is written in controllable canonical form in this format, and the eigenvalues of the matrix A are lambda 1, lambda 2, all the way to lambda n, which are distinct. In other words, there are no repeated eigenvalues. We can obtain a transformational matrix P. We can obtain a transformational matrix P from the eigenvalues of the matrix A as follows. The matrix P will be given by the first row will be a row of ones as 1, 1, all the other terms being 1. The second one will be lambda 1, lambda 2, all the way to lambda n. The third one will be the squared terms, lambda 1 squared, lambda 2 squared, all the way to lambda n squared. And the last row will be a row of lambda 1 raised to the power of n minus 1, lambda 2 raised to the power of n minus 1, all the way to lambda n raised to the power of n minus 1. This is our transformation matrix P. The transformation matrix P obtained from the eigenvalues of the matrix A is going to transform the matrix A into diagonal form, such that our transformed matrix A hat, which is obtained by P inverse AP, will be in diagonal form. Therefore, in diagonalization, we are looking at the formation of a transformation matrix P from the eigenvalues of the matrix A given in this format, so long as the matrix A is written in controllable canonical form and has distinct roots. If this happens, then the transformation of the matrix A will be into diagonal form. And this is the concept of diagonalization. I will take this in form of an example for illustration purposes. Consider a system described by the state space representation. Consider a system described by the state space representation, x1 derivative, x2 derivative is equals to 0, 1, minus 2, minus 3 into x1, x2 plus 0, 1, u, and our y of t is given by 1, 0, x1, x2. We are supposed to obtain the state space representation of the system in diagonal form using the concept of diagonalization. Okay, so we use the concept of diagonalization to transform the system state space representation into diagonal form. From this, we notice that our matrix A is 0, 1, minus 2, minus 3, which is written in the format of the controllable canonical forms, 0, 1, and then the last row is a row of the coefficients of the characteristic equation. From this, then, we can determine the eigenvalues of the matrix A by solving for lambda I minus A determinant is equals to 0, from which we'll have lambda minus 1, 2, lambda minus 3 determinant is equals to 0, which will give us lambda squared minus 3 lambda plus 2 is equals to 0. Look at this, then the roots of the factors are -1 and -2. So we can write lambda minus 1 into lambda minus 2 is equals to 0. And therefore, the roots of the equation, so this is supposed to be plus 3. You look at this is lambda plus 3. So this becomes positive. Then these terms becomes positive 1 and positive 2. And therefore, the roots are lambda 1 is equals to 1 negative, and lambda 2 is -2. Those are the eigenvalues of the matrix A. We determine a transformational matrix P from the eigenvalues of the matrix A as, so our matrix P is supposed to be a matrix of the first row, which are ones, the second row, which are the roots, lambda 1 to lambda n. And because this is a second order system, therefore, our matrix P will be a 2 by 2 obtained as 1, 1, lambda 1, lambda 2, which will be the matrix 1, 1, -1, -2. To carry out the transformation from the given state space representation into diagonal canonical form, we carry out the transformation. A hat will be given by P inverse AP, which will be 1, -1, 1, -2, inverse multiplied by A, 0, 1, minus 2, minus 3, multiplied by 1, -1, 1, -2. And this one will give us 1 over the determinant. The determinant will be -2, and then plus 1, which will be -1. So in other words, we'll end up with -1. So we'll have -1 into, then we interchange this to -2, 1. We negate this to 1, -1. We multiply this by, this will be 0, -1. This will be 0, -2. Then this will be -2 plus 3, which is 1, and minus 2 plus 6, which is 4, which will give us, this is 2 minus 2 minus 1, which is okay, sorry. So this one will be, this is 2 minus 1. This is 1, and because of this negative, we'll get negative 1. Then this one will be 4 minus 4 is 0. We'll get this as 1 minus 1 will be 0. And this one will give us minus 2 plus 4 is 2. Because of the negative, we get that to be negative 2. And that is our matrix A. Our matrix B will be given by P inverse B, which will be, the P inverse is this matrix, negative 1 into minus 2, negative 1, 1, 1, multiplied by matrix B, which is 0, 1, which will be equal to, the matrix will be, this will be 1, this will be negative 1. The matrix C will be given by, or C hat will be CP, which will be, the matrix C is 1, 0, multiplied by the matrix P, which is 1, negative 1, 1, minus 2. And this will give us, this is 1, 0. So this is 1. This is 1, 0. This is 1. That is our matrix C, from which we can write the state space representation of the system as follows. X1, X2 derivative is equals to the matrix A. The matrix A is obtained as negative 1, negative 2, a diagonal matrix. So negative 1, 0, 0, negative 2 into X1, X2 plus the matrix B. The matrix B is given by, matrix B is 1, negative 1. So our matrix B is 1, negative 1, U, and our Y of T is given by the matrix C. The matrix C is 1, 1. So this is 1, 1 into X1, X2. And as you can see, this transformation transforms the state space representation of the system into diagonal form using a suitable transformation matrix P obtained from the eigenvalues of the matrix A. And as you can see, the matrix P was determined from the eigenvalues of the matrix A, and through this we are able to diagonalize the state space representation of the system, and that is the concept of diagonalization. Thank you for watching the video.